back. Any questions on the previous material or on the homework? Okay, no questions. All right, let me try to remind you what we did last time. So last time I was talking about these bounded affine permutations, which I guess I'm not really going to need them in this lecture, but still let me just say that a bounded affine permutation f is just a bijection from z to z satisfying some conditions. Bounded affine permutation. The conditions are shown here, and B of k comma n is the set of such kn bounded affine permutations. In particular, the most important one is the top cell bounded affine permutation, which is denoted fk comma n, which sends fkn of I is just equal to I plus k for all I in Z. So so for this most important remember for each f in this set, there is a positroid cell. You pick a graph with this strand permutation, and then you look at the boundary measurements. So what is the positroid cell for the graph G, such that the strand permutation of G is this top cell bounded affine permutation? Well, it's going to be PG bigger than 0. In general it's some subset, right? All positroid cells, they stratify this totally non-negative Grassmannian, and actually it turns out that this positroid cell is the totally positive Grassmannian. So it's the whole interior of your totally non-negative Grassmannian. Whenever your strand permutation is the top cell, then so this stratification of the totally non-negative Grassmannian has a unique kind of unique top dimensional cell. Right? It has a dimension of pi g bigger than 0 is k times n minus k, and that's the only one that's top dimensional. Which yeah, so by the way, in general if G is reduced, then the dimension of the corresponding positroid cell is equal to the number of faces of G minus 1. Somehow there is an Euler's formula argument which shows that the dimension of the positroid cell is the positroid cell is homeomorphic to an open ball of this dimension. For example, in particular, if G corresponds to the top cell, then the dimension of P sub G is what? Or let's say I write it another way. What is the dimension of the totally positive Grassmannian k comma n? Right, thank you. It's k times n minus k. And in particular, the therefore the number of faces of your graph G is equal to k times n minus k plus 1. So for whenever you have a reduced graph with a given strand permutation, then the minimal number of faces it should be given by this k times n minus k plus 1. So for example, let me try to draw. Let's say I do k equals to 2, n equals to 4. And then my graph looks like this. I'm not going to draw the boundary vertices soon, but it looks like this. So what is the number of faces? 5. And what is k times, k times n minus k plus 1 is also 5. So once you check that the permutation, that the permutation is the strand permutation is correct, and once you check the number of faces, you're good to go. You've got a graph for the top cell. And let me show you another example. Let's say I do k equals to 2, n equals to 5. And then I guess I should do something like this. I always confuse the colors with this one. So far this is the non-reduced graph from the last lecture, but if you take the reduced one, you add this extra boundary edge, then you can check that the strand permutation always adds 2 modulo 5, right? I don't know if that looks convincing or not. And then you can count the faces. So how many faces of this guy do we have? 7. Okay. Wait, what? Okay, 7. And I guess k times n minus k plus 1 is also 7, hopefully. Yeah, so the conclusion is that these two graphs are reduced. Yeah. So now there is an important move for Plavik graphs for Plavik graphs, which basically any two. Let me describe the move, and that's called the square move. So and I think it's beautiful. So what is the square move? Whenever let's say you have found a face which you have found a square face, then the rule is that whenever you have a square face, you can flip the colors of the vertices, and that's called the square move. But you have to be careful. So let me be careful here. So let's say you have a square face. Well, in principle, these vertices have a lot of other neighbors. So what you do first is you uncontract. You uncontract the so that your graph is no longer bipartite, but so what you want to do is you want to uncontract so that all vertices of this face have degree 3. All right, so uncontract so that all vertices are trivalent, and then you swap the colors. So you swap the colors. This is now black and black, and this is white and white, and then you contract the unicolor. So let's maybe this vertex was black, what was white, and this is also white, and this is also white. Then when you contract, you want your resultant graph to be bipartite. So the answer is gonna I'm gonna just contract this edge on the right, and that's gonna be so this operation takes a planar bipartite graph and produces another one. It's called a square move. Okay, and if you so if you look at the original graph and you look at the one you got after the square move, well, what happens to the strand permutation? What happens to the strand permutation? What do you think? Okay, yeah, that's a good guess. So hopefully the strand permutation is the same, but is it actually the same? Let me try to draw a few strands. You start here and you go left, right, left, and you end up here. While on the right you go right, left, right, and you end up here. And yeah, maybe should I draw another one? You go right, left, left, and you end up here, and then you go right, you go right, left, and you end up here. So you can see that if I kind of outside of this square, the strand permutation is the same. Right? You can draw all the other strands, like this goes right, left, right. Wait, what? No, sorry. This goes left, right, left. Yeah, so there is a strand that goes like this, and then the same strand goes like this. So you can see that sort of the behavior of the outside strands is preserved. And so an actual example for k equals to 2 and n equals to 4 is that you start with a graph that looks like this. And then you apply the square move and you get a graph that looks like this. And these two graphs have the same strand permutation, and both of them are reduced. Both of them have the same number of faces, right? I mean, if it has the same strand permutation and the same number of faces, then it has to be reduced. So, so that's the square move. And then the theorem is that any two reduced graphs are related by square moves if and only if they have the same strand permutation. Any two reduced graphs G and G prime are connected by square moves if and only if they have the same strand permutation. So maybe I should I try another example? Maybe I should try this one. Yeah. So this graph has two square vertices. So I have two square moves that are available. Let's say I pick one of them. Let's say maybe I take this vertex here. Oops. Yeah. I take this vertex here and apply the square move. So first I have to do what? Okay. Yes. Thank you. I have to uncontract the white. I don't know why that didn't work. I have to uncontract the white vertex. So let me try to do that. Okay, and now all vertices are trivalent, and then I can swap the colors. well, I guess there's one more complication that's going. I'm gonna have to. Okay, but let me first. So I swap the colors. No, these are now white, and these are black, and then I contract, the extra edge. Okay, so that is the square move. And hopefully what you see is that I got the same graph. But it's sort of rotated a little bit. Yeah. Somehow applying a square move to this graph produces the same graph modulo rotation by. You basically rotate by 2. So if you keep applying these square moves, you're going to get basically 5 graphs, which are all rotations of one another. And these are all possible reduced square graphs for k equals to 2 and n equals to 5. So there's 5 of them. And yeah, I'm going to discuss later somehow what you should think, what should appear in your head right now is triangulations of a pentagon. There's 5 triangulations of a pentagon, and they form kind of a cycle under if you flip the diagonals. Anyway, I'm gonna explain this in detail. Yeah, but for now, I guess I should also mention. Yeah, I should mention that the square moves. I'm not gonna explain this, I think, but the square moves preserve. Well, I did say that they preserve the strand permutation, but they also preserve the Positroid cell. There is a way to, if you have some edge weights on one graph, then after you apply a square move, there is a way to assign weights to new graphs such that the boundary measurements are preserved. So the square moves literally act on weighted planar bipartite graphs. Okay, and now I'm slowly going in the direction of cluster algebras. But for now, let me also, I just enjoy studying the combinatorics of such graphs. So let me tell you a little bit more combinatorics towards this goal of cluster algebras for Grassmannians. And that is the phase labels. The phase labels, well, what I'm going to do is I'm going to take a planar bipartite graph. Let's say I take this one. Phase labels. Here's my graph again. Let me label the boundary vertices B1, B2, B3, B4, and B5. And what I'm going to do is I'm going to label each face. Label each face by a k element set. So inside of each face, I'm gonna have a 2-element set. So how do I label? Well, the rule is very simple. So for each strand, which goes from bi to bj, you add j to all face labels to the left of the strand. So let's see what's going to happen. Let's say I consider this strand that goes 4, left, right, left, and terminates at 1. So what should I do now if it terminates at 1? Yeah, that's hard to explain in words. It terminates at 1, and then I have to put 1 everywhere to the left of the strand. Is that clear? let me, so 1, 1, 1, 1 is to the left of this strand. Now I consider the strand that goes left, right, left and terminates at 2. So I put a 2 in these two face labels. And now I keep, let me just finish this example. Right, left, right, left, right. B1 goes to B3, so you put a 3 in all these face labels. 3, 3, 3, 3. And then 2, left, right, left goes to 4. So you put a 4 in these two face labels. Finally, the last one goes right, left, right, left. So you have a 5 in these three face labels. So I got a k element set inside of each face, which is very nice. And if you think about these sets, yeah, these two element sets are actually, they give you diagonals of a triangulation, by the way, which again I'm going to explain this later, but yeah, 1, 3 and 3, 5 are diagonals of a triangulation. Now yeah, I guess now is the time to explain this bijection. So yes, example, when you take the top cell for the permutation f2, n, then the reduced planar yeah. Did I use the word playback before, or is it the first time I'm using it? Used it before. Thank you. Reduced playback. I thought I used planar bipartite, but the playback actually means, I don't know if I said this, it means planar bicolored. It's not quite bipartite because you allow, sometimes people allow having edges which connect white vertex to connect unicolored vertices. But for the dimer model, we forbid that to happen. So reduced playback graphs are in bijection with triangulations of n and gone. Yeah. So what is the bijection? Let's say I'm going to try this. Okay, I haven't tried this at home, so I may not be able to do this properly. So let's say you take a triangulation. Then what I think you should do is you should put a black vertex on every vertex. It's either black or white. But let's say you put a black vertex on every vertex of your triangulation, and you put a white vertex in the middle of every face of your triangulation. And then inside, so each face, you have these triangles. Inside each triangle there is a white vertex and 3 black vertices. So you connect the white vertex to the corresponding 3 black vertices. And then I think that's it. You just kind of, then you draw n boundary edges, and then you erase the triangulation. Right, I think with the right convention, yeah, let's see if I have 1, 2, 3, 4, 5, then what are the face labels? Yeah, 4 goes to left, right, left, right, left. 4 goes to 2. Okay, then I messed up the colors. 4 has to go to 1. Okay. All right, let me fix the colors. this is going to be all white. This is going to be all white. And then this is going to be all black. One of the conventions is going to work. Okay, so now 4 goes right, left, right. Yeah, 4 goes to 1 now. So this works. 4 goes to 1 like this, and so I put a 1 in these labels. Now 5 goes to right, left, right. 5 goes to 2, so I put a 2 in these 3. 2, 2, 2. 1 goes to 3, so I put a 3 to the left of that strand. 2 goes to 4, so I put a 4. Yeah, and finally 5 goes, 3 goes to 5. So I go left, right, left, and I get 5 and 5. So yes, first of all, the boundary vertices are always going to be just kind of cyclic intervals. They're going to be the sides of your polygon. And the things in the middle, yeah, that's an exercise. So you get 2, 4, and 1, 4, which is slightly different from the diagonals I had. I guess you have to shift, you have to add. So I had 1, 3, and 3, 5, so you have to add 1 to all those numbers. My diagonals were 1, 3, and 3, 5. And the face labels are 2, 4, and 4, 6, which is actually 1, 4 modulo 5. Yeah, so an exercise for you is to show that, prove that it works in general. Well, in general, I mean still k is equal to 2, but just arbitrary triangulations. But yeah, the point is that the reduced graphs are in bijection with triangulations, and what do the square moves correspond to? Yeah, the flips of, yeah, flips of triangulations. So I don't know if I should, yeah, maybe you should, maybe it's also an exercise to, maybe yeah, I should make this all a big exercise. So exercise is you apply your square move, and then you see that instead of 2, 4, you're going to get some other face label, which is going to be the other diagonal in your triangulation. So yeah, anyways, this all works very nicely. You kind of you literally get what I mean. It's called the associahedron. Right? You have triangulations which are connected by flips. You get the same structure for reduced Playback graphs for this permutation for the top cell, and you don't get any other reduced Playback graphs. And by the way, let me now ask a general question. So I mentioned that the boundary labels are for triangulation are always going to be the sides of an n-gon. So question is, what's going to happen in general? So if I give you a permutation, let's say given a bounded affine permutation f, what are the boundary face labels of G? So you have your graph G, and then you have n boundary vertices, B1, B2, all the way up to Bn. And each of them is black of degree 1. So you naturally have these face labels, right? And some of them could coincide, but in general you have these n face labels, which I'm going to denote. I guess I'm going to denote this one by I1, I2, I3, all the way up to IN. Okay, so I get a sequence I1, I2, all the way up to IN, a sequence of k element sets. Question is, given your permutation f, how do you describe these sets? And by the way, the sequence of sets is called the Grassmann necklace of f. Right, okay, so you're saying for k equals to 2, you have I and I plus 1. Okay. Okay, yeah, that's a good observation, right? Whenever, let's say I draw the boundary. Let's say here I have BI, and then I have a strand which terminates at BI. And then I have the face label that's immediately left to BI, which is labeled by, well, okay, let me say instead of BI, let's say I call this BR. So I don't have, so I have IR. And then because the strand terminates at BR, R has to belong to this face, right? So okay, so you're saying if the strand starts here, then yeah, that's actually the strand starts here, then it belongs to the next one, right? But it's not labeled by R. Let's write it down. I think that's IR plus 1. So okay, if I have a strand which starts at BR, where does it terminate? Right. Yeah. So you have to include whatever is bx. If it terminates at bx, then you have to include x into this set, right? I think. Okay. Yeah, I think that's the correct get, right? So you have your set IR, and then you look at all these. You look at all strands which such that IR is to the left of them, and that basically the permutation tells you what this IR is. In particular, let's finish this example, right? If your strand starts at BR, it has to terminate at BF of R. Right? That's just by definition of the strand permutation. So in particular, and you can see that these are the, other than these two strands, IR and IR plus 1 are the same. So IR plus 1 is equal to IR. What do you do? You remove R, and then you add, well, you remove R, and then you add f of R. That's the rule for the Grassmann necklace. Or in other words, you can kind of draw the diagram of f. Let me actually, I think that this is a good time to explain this in terms of the bounded affine permutations. So remember, my bounded affine permutation satisfies something like I less than or equal to f of I less than or equal to I plus n for all I. Right. So the strands point to the right. And let me try to draw some example. 1, 2, 3, 4, 5. Let's say I draw some permutation. Or maybe, can somebody tell me a permutation? Just the usual permutation in a sun. Okay, who's brave enough to say 5 numbers? Three, 5, 4, 1, 2. Thank you. 3, 5, 4, 1, 2. Okay, then I'm gonna draw the bounded affine permutation. So 1 goes to 3, 2 goes to 5, 3 goes to 4, 4 goes to 1, 5 goes to 2. Yes, thank you. This is a great bounded affine permutation. So question is, what is the Grassmann necklace of F? Just purely in terms of the affine strand diagram. Let me even duplicate it so that all right. So so what is the rule? And the rule is very simple. The rule for IR, to determine IR, what to do is you look at the indices R, R plus 1, etc. in your bounded affine permutation. So your bounded affine permutation kind of looks like this, maybe something like this. So you kind of draw a vertical line which separates R from R minus 1. And then you just look at all the indices which, so remember there is one of the characterizations of these bounded affine, one of the conditions on these bounded affine permutations is that the sum is equal to k times n, which is the same as saying that when you draw a vertical line, there's going to be exactly 2 strands which intersect your vertical line. And the corresponding indices are the Grassmann necklace of your so in particular for this permutation F, can somebody tell me what is I1 of this F? One, 2. Okay. Indeed, I draw this vertical line and I see 1 and 2 that intersect. I1 is 1, 2. And yeah, for I2 I get 2, 3. I3 is what is I3? 3, 5. Okay. 3, 5, and I4 is, I guess, 4, 5, and I5 is finally 1, 5. Yeah, so these are the boundary going to be the boundary labels of your Plavik graph corresponding to F. And somehow these are also important in determining the kind of the Positroid cell corresponding to F. So yeah, let me denote. So what I'm going to denote the Grassmann necklace by this fancy I sub F, just by definition I1, I2, etc. up to IN. These are the boundary labels. And just to write down the actual definition of, I mean, it's basically the same thing as I just said here, but I sub j is by definition consists of all f of I such that I is strictly less than j and less than or equal to f of I. Right, that's the same. I guess I used r here, but it's the same. So I'm taking all indices which start strictly to the left of r, but terminate weakly after r. That's the same. Is it clear that it's the same formula? Okay, I see. All right. So now let me use, well, in particular for the, okay, what happens for the top cell? Let's say in general fkn. What is the Grassmann necklace of fkn? Yes, thank you. That is correct. So r is r plus 1, all the way up to r plus k minus 1. Well, modulo n. These are the cyclic intervals of size k. These are the Grassmann necklace for the top cell. Okay. Now I can whenever I get some new combinatorics for Playback graphs, I can spit out some more facts about total positivity. So you have a question. Right? You have a question of what is the Positroid cell? How to describe the Positroid cell? Which I'm gonna, from now on, I'm just gonna denote Positroid cells by pi sub f. So what I do is I choose a reduced graph for f, and then it doesn't matter which one I choose because they're all related by square moves. So it basically only depends on your bounded defined permutation f. In terms of f. Which, okay, so the more precisely, I have the total negative Grassmannian is the place where all Plucker coordinates are non-zero. And what I'm gonna say is that pi sub f is the set of all elements in the totally non-negative Grassmannian such that delta I of w, or let's say delta j of w is strictly positive if blah blah blah, and delta j of w is 0 otherwise. So each Positroid cell is going to be the subset of this totally negative Grassmannian, where I just prescribe some Plucker coordinates to vanish and the others to be strictly positive. So question is, what is this extra condition that you should somehow only depend on your bounded defined permutation f? And that's, I don't know if somebody has a guess, but that's actually hard to guess. So let me, I think I have the time to explain that today. And the condition is as follows. So first you introduce the Gale order on k element sets. It's given as follows. If you have two sets, I, which consists of I1 less than I2, less than etc., less than ik, and j, j1, j2, jk, then I say that I'm going to try to draw a fancy less than or equal to j if I1 is less than or equal to j1, I2 is less than or equal to j2, and etc. Ik less than or equal to jk. So it's the term-wise order on the sets, called the Gale order for some reason. And so that's going to be the main type of condition, except that I'm going to have to introduce a cyclically shifted Gale order. So let me be precise here. Let's say I fix some index r, and then I consider the total order, which I'm going to denote less than or equal sub r on the indices from 1 up to n. And that's just the cyclically shifted usual order. R less than or equal than r plus 1, less than or equal than r plus 2. At some point it wraps around, and then eventually you run into r minus 1. So with respect to my new order, r is the minimal element and r minus 1 is the maximal. And these are all actually strict. I'm trying to make them into strict inequalities. Okay, and then the same definition applies. So I fancy less than or equal r sub r of j if, let me just copy. I'm just going to copy the same stuff, and then I'm going to put r everywhere. So r. Does it make sense? So I'm just cyclically shifting the whole definition. And finally, let me define the positroid of. So that's an important definition. The positroid m sub f. So the positroid is going to be a collection of k element sets. Is given by, so it's defined as follows. It's just the set of all j in n choose k. It's going to consist of all such j's such that such that ir is fancy less than or equal sub r of j for all r from 1 up to n. So I'm taking ir, so where the Grassmann necklace of f is I1, I2, I sub r. So in other words, I'm using the Grassmann necklace to define a collection of sets, which is called the positroid. And if you know what is a matroid, then a positroid is like a positively oriented matroid. So it's a special kind of a matroid. A matroid is a collection of bases. Yeah, anyways, never mind. But it is a matroid. That's, I guess, one message that I want to say just to justify the name of this. Now I finally can describe the Positroid cell. The Positroid cell, pi sub f bigger than 0, just consists of all, did I use w? Let's say v, such that delta j of v is bigger than 0 for j inside the positroid, and delta j of v is equal to 0 otherwise. I see that people are not impressed, but I mean, whatever. The point is that I'm only doing combinatorics. I have these bounded defined permutations, which are combinatorial, and then I define these Grassmann necklaces, which are combinatorial, and then I use the Gale order to define the positroid, which is combinatorial, and what I arrive at is a complete description of a complete stratification of the totally non-negative Grassmannian into positroid cells. In each positroid cell, you just specify which minors are strictly positive and which minors are exactly 0. So the claim is that if you take any reduced graph with this strand permutation, you will get exactly all elements of the Grassmannian where these minors are positive and these are 0. I guess that is the conclusion. Okay, some people are impressed now. All right, I'm out of time, so I will pre-record another lecture. I will see you next Wednesday. Have a nice weekend. If you have any questions, let me know.